Okay, let's talk about polar form of complex numbers. And the basic idea here is not really about complex numbers at all. The basic idea is this. If you're looking at coordinate axes and you have a point, usually we give that point, we locate that point, we tell you where it is by giving an x and a y coordinate. Yeah? Whoopee. Okay, that's the typical way that we look at it. But I could also tell you where that point was by doing the following. If we can imagine starting at the origin at 0, 0, and then drawing a line from there out to my point, if I tell you the length of that line, let's call that r, and I tell you the angle that this thing makes, we'll call that theta, well, by knowing theta and r, you can also find that same point. So if I'm trying to describe to you the location of this point, one way to do it would be to give you an x and a y coordinate. Tells you how far to the right and how far up, over and up. That's your x and your y. Okay, but another way to find that same point would be to describe it using an angle and a distance. And this is exactly what we want to do with complex numbers. Why do we want to do this? As it turns out, complex numbers, there are certain aspects of them that are just make an amazing amount of sense when you look at them in this form. When we write a number in the form with distance r and an angle theta, we call this the polar form of the number. And that's what we're going to be talking about today. We'll introduce the polar form of a number, and we'll talk about how we convert back and forth. If I give you the standard form with a and b, so for a complex number, this would be like a plus bi. How do we come up with the polar form? What does the polar form really look like? A few vocabulary words here. This number r, which is like the distance from your point to the origin, r we often call the modulus. Whoops. There's an accident. There we go. R. This is modulus. And the angle we often call the argument. So if we're talking about a complex number, a plus bi, then when we want to express it in polar form, what do we want to find? We want to find the modulus, the r, and the argument, the theta. So that's what we're going to want to do. That's our goal. All right, let's go ahead and look at a slightly more prepared picture of this same scenario. So this is just from your book, from the lesson online. Here you can see we have the complex plane. The real axis is the x-axis, the imaginary axis is the y-axis, and here we have a point a plus bi. If we wanted to write that in coordinates, we would write it a comma b, writing it in standard complex form a plus bi. That's this point right here. And if we think about making that line back to the origin, and then about making a triangle out of it by dropping a vertical down there. This should be sort of familiar from our work in trigonometry. Well, what do we know about the triangle as such? If you think about the sine of this angle, sine is equal to the opposite over the adjacent. So sine is equal to this y value divided by r. And cosine is equal to this x value divided by r. And we can flip those around to get what is the y value. Well, the y value then is r times the sine of the angle. And the x value is r times the cosine of the angle. What do we have here when we're looking at the point a plus bi? If you would like to understand where these coordinates a and b come from in terms of r's and thetas, the a, which is the x-coordinate, is equal to r times cosine theta, and the b, which is the y-coordinate, is equal to r times sine theta. Okay. So, in general, if we want to take a number a plus bi, this right here is standard form. If we just replace a with r cosine theta, I apologize. I'm going to switch to black here because it's going to be much easier to read. We'll get rid of that guy and that guy. Okay. So we have a plus bi. That's our standard form. Let's replace a with r cosine theta. And then plus, and then b times I. b is r sine theta times I. So that's just substituting in the two formulas above. And then what you'll notice about this expression is, number one, it has something in common, the two terms. They both have r in them. So we're just going to pull that r out into the front. And second, this I, instead of writing it after sine, I'm going to write it in front of the sine. We do that. It's the sort of the standard way to do it because we don't want the I. We don't want to get confused and think that that I is in with the theta multiplied by the theta. It's not. It's multiplied by the entire sine theta. So let's just do one step of simplification. This is r times cosine theta plus I sine theta. And when we take our original complex number in standard form, find r and theta, and then rewrite it in this form, we call this the polar form of that same complex number. So this expression and this expression, they are talking about the same complex number. They're talking about the same point in the complex plane. It's just that here, that point is being given to us with the a and the b, which is like the x and the y coordinates. And here, that point is being given to us in this expression that involves r, that distance to the origin. And then the angle, cosine theta plus I sine theta, the angle in there is the angle from the positive x-axis or the positive real axis up to that line that goes out to our point. So, what do we have so far? We have the definition of polar form of an angle is this guy right over here, and then that's the standard form of the angle on the left. Okay. Our next challenge is going to be, suppose I give you, well, if I give you r and theta, that is to say, if I describe a complex number by giving you the r and the theta, giving it to you in polar form, we can convert it back into standard form by just using the two formulas here. Plug in r times cosine theta and r times sine theta, and that will find you a and b, and then just write it as a plus b times I. Okay. That's how we would convert from the r's and thetas from polar form into the standard form. What we want to be able to do is do the opposite. If we start with a number in standard form, how do we find r and how do we find the theta so that we can rewrite it like this? Okay, that's what we're going to work on next. These are going to be formulas for converting from polar form, from standard form, from the a's and b's, into polar form. So, just as a reminder, when we're talking about our polar form, that number r, we call that the modulus. And the theta here and here, that's called the argument. And the argument appears twice in polar form, and if you're given a complex number like this and those angles, the arguments are different, then it's not a complex number in polar form. You need to do some further work to simplify it or something else. They have to be the same angle in both cosine and sine there. Okay. Converting from standard form to polar form. These are the formulas that we are going to use. So first of all, this r. And remember, what we want is a formula that involves the numbers a and b. So this bottom is given by a, that's r cosine theta, but we're assuming here we have a and b to work with. So that's a and this is b. And we're going to use the Pythagorean theorem to say that a squared plus b squared is equal to r squared. If a squared plus b squared equals r squared, then to get r by itself, we just take the square root on both sides. That r is equal to the square root of a squared plus b squared. When converting from standard form to polar form, the other thing that we want to pay attention to is that angle theta. And I don't have a formula for the angle, but what I can tell you is if you know A and B, that is A and B, let me see, the tangent of this angle, tangent is exactly opposite over adjacent. So the tangent of this angle is equal to this guy, that's B, divided by this guy, that's A. So that's the formula that we're going to use. Tangent of theta, if you want to know the argument theta, well, I can tell you what the tangent of theta is. It's equal to B over A. So these are the formulas that we're going to use to convert. If we have a number a plus bi and we want to find the r, the modulus, and the theta, the angle, or the argument, these are the formulas we're going to use. To find r, pretty straightforward. You just plug in and take square root of a squared plus b squared. That gets you r. To find theta, we have to be a little bit careful here because what this will tell us, b over a, tells us the tangent of theta. And if we know what the tangent of theta is equal to, how do we find theta? There's an obvious answer, which is that theta is just the arctangent, or the inverse tangent, of b over a. And that is almost true. That might be true. I'm going to put a little question mark over it. The only trouble is that the inverse tangent always gives you answers in the first quadrant or the fourth quadrant. And so the trouble here, this is in quadrants 1 and 4. And our problem is, if our angle lies in quadrants 2 or 3, what do? Well, we have to take the angle in quadrants 2 or 3 that has the same angle, the same tangent as this angle that we've been given. So the arctangent gives us an angle, and we want an angle that has the same tangent as that, but in quadrants 2 and 3. So quadrants 2 and 3. How do we do it? Well, we just take that arctangent b over a, and if it's in radians, we add pi. Adding pi is like going halfway around the circle. That'll get you into quadrants 2 and 3. If we're working in degrees, then it would be a similar thing, arctangent of b over a. But here, instead of adding pi, we would add 180. So that's in degrees. And basically what you'll find is that to find theta, theta will either be equal to the arctangent, or if this happens to be in the wrong quadrant, it will be equal to the arctangent of b over a, either plus pi or plus 180, depending on whether you're working in radians or degrees. All right. You will see this in action when we look at the next example and see exactly how this calculation works. Okay. Let's go ahead and do some examples. Convert the number to polar form. So we're given a number in the form a plus bi, and we would like to write it. Recall, the polar form is the form r times cosine theta plus I sine theta. That's what we would like. So let's take a look at part A. Part A, 2 plus 3i. Well, we need to find two things for this. We need to find the distance, or the modulus. To find the modulus r, we just use the formula r is equal to, this is the one circled up above, r is equal to a squared plus b squared, here. So we know a and b, a is 2 and b is 3, so r is the square root of 2 squared plus 3 squared. This one we can simplify in our heads. This is radical of 4 plus 9, which is equal to radical 13. And of course, if we wanted a decimal version, we could use a calculator to get radical 13. Since 13 doesn't have a nice square root, we're just going to leave it like that. So we have found r. Now we want to find theta. To find theta, we need to find the arctangent of b over a. Well, b over a is 3 over 2. So this is the arctangent of 1.5. This is not a value of tangent that pops immediately to mind. This is not one of the ones that I just know off the top of my head. So we plug it into a calculator, the arctangent of 1.5. Now, I'm going to work now in degrees. And so it's going to be important that we set our calculator into degree mode so that it gives us the angle arctangent 1.5 in degrees. If we do that, then we should get plug arctan of 1.5. Remember, your calculator may also say this instead, tan inverse. It's the same as arctangent 1.5. So we want to do one of those two, and just make sure your calculator is set into degrees. We'll keep just a single decimal point. This is 56.3 degrees I get by my calculator. Okay. Now, the question is this the correct angle theta? And here's how we figure it out. If we draw the coordinate plane, the number 2 plus 3i, if we just graph that in standard form, 1, 2, and then 1, 2, 3, here is the number 2 plus 3i, and I see that it is in the first quadrant, quadrant 1. And then when I look at this, 56.3 degrees, this is also an angle in quadrant 1. How do I know that that's in quadrant 1? Well, if we're working in degrees, 0 degrees is here, and 90 degrees is here, and ours is between 0 and 90. So 56.3, it's somewhere in here. It's exactly this guy. And so I can tell that this angle that I've got is in the correct quadrant. I don't need to do any adjustment, and that tells me that theta is equal to 56.3 degrees. Now, this is only approximately 56.3 because when I took that inverse tangent, I rounded it off. So it might be better to do the squiggly equals approximately 56.3 degrees. So we have found r, we have found theta. All we have to do is just combine them into this form in order to get the polar form of this complex number. So when we write it 2 plus 3i, that's standard form. In complex, in polar form, it's equal to radical 13 times cosine of 56.3 degrees plus I times sine of 56.3 degrees. This is the polar form of this complex number. Okay, go ahead, pause the video now, work through parts B, C, and D, and then come on back and we will work through them together. Okay, let's do it. Part B. This is minus 2 radical 3 I. Just to get a sense of where this thing is, if we think of it in standard form, then a plus bi, the a is negative 2, that's like my x-coordinate, and b is negative 2 times radical 3. Now, what is that exactly? I don't know. You could use a calculator to find it, but it's certainly negative, and that's our y-coordinate, probably around negative 3 or 4, something like that. I don't care too much about precision. I'm just using this to get an idea of what quadrant this is in. It's in quadrant 3. This is our point here, minus 2 radical 3 I. Okay. So that's just a good observation. Now, let's imagine we're starting this negative 2 minus 2 radical 3i. We need to find two things. We need to find the modulus, and that's r is equal to the square root of a squared plus b squared. A is negative 2 squared plus b, which is negative 2 radical 3 squared. So we can simplify this thing. It's radical. Negative 2, when we square it, becomes positive 4. Negative 2 times radical 3 squared, you can square each of them. So this is negative 2 squared is positive 4, and radical 3 squared is 3. This is radical 4 plus 3 times 4 is 12. This is radical 16. And radical 16 is 4. Now, notice the modulus, the r, is never negative. It's always positive or 0. And so it's okay. We don't have to worry about a plus or minus. There's no plus or minus in the formula. It's just always the positive answer that we get here. So our r is 4. That's a nice, simple solution for our modulus. Now let's find the argument, or the angle. Well, what we know is that the tangent of our angle is equal to b over a, which is negative 2 radical 3 over negative 2. The tangent's equal to that. Well, we can do a little simplifying on the right-hand side there, so we have that tangent theta is equal to, the negative 2's cancel, and they leave behind just radical 3 over 1, or just radical 3. So tangent of theta is equal to radical 3. Okay. This is one of the values of tangent that appears in our table of basic values. If you don't remember it, go back and read that table and put it into your head. Radical 3 is the tangent of the angle pi over 3, or 60 degrees. I'm going to work in degrees in this problem, so let's say that theta equals 60 degrees, and that's from the basic trig functions, trig function values. Okay. Is theta equal 60 degrees? That is the inverse tangent. That is an angle whose tangent is radical 3. But I'm going to put a question mark by it because here's the issue. 60 degrees, well, that's between 0 and 90, so that's between 0 here and 90 here. That's in the first quadrant. And our number, negative 2 minus 2 radical 3i, is in the third quadrant down here. So this is the case where we have to use the idea, if this is in the wrong quadrant, this is quadrant 1, so we're going to do what? We're going to find the angle that is directly 180 degrees around the unit circle from this. That'll take us from quadrant 1 around 180 degrees to quadrant 3. That'll get us to the place that we need. And how do we do it? We just add 180 degrees to the angle. So this is 60 plus 180. 60 and 180 is the angle 240 degrees. And if you think about in the unit circle, here's 0, 90 degrees, 180, 270, 240 is going to be in here in the middle. It's going to be in quadrant 3. That's just a good reality check that this is the angle that we want. So that's quadrant 3. Now, we've found the modulus, and we've found the argument. That is to say, we found the distance and the angle. Let's go ahead and put them together to give the polar form of this number. So this number minus 2 radical 3i is equal to, in polar form, is equal to 4 times cosine 240 plus I sine 240. And I'll label those degrees just to make sure we don't forget we're working in degrees here. Here is the polar form of this number. Pause now if you want to work through C and D on your own, and then come back and we'll do them. Here we go. Oops. Give myself just a little more room here. So, part C, 4 minus 3i. Let's do it. Okay. First of all, this is, if we were to graph this, the x-coordinate is 4, that's the A, and the y-coordinate is -3, that's over here, 4, comma, -3. This is in quadrant 4. That's 4 minus 3i. Okay, quadrant 4. Let's see, 4 minus 3i, let's convert this to polar form, so we need to find the modulus r. That's equal to the square root of a squared plus b squared, so the square root of 4 squared plus -3 squared. And that's the square root of 16 plus 9, which is the square root of 25, which is 5. So we have a nice modulus, r equal 5. Let's just record that and stick a box around it for later reference. And now let's find the angle, the argument, theta. To find theta, well, we know that tangent of theta is equal to b over a, so that's equal to -3 over 4. And -3 over 4, this is not a value of tangent that I know off the top of my head, so I'm just going to go ahead and use the arctangent or inverse tangent function to see what kind of angle gives me a tangent of -3 over 4. When we plug this into the inverse tangent or the arctangent function, we get a value in decimal of approximately -36.9 degrees. Now, reality check. Where is this angle -36.9 degrees? If we look on the unit circle, this is 0. Negative angles go this way. This is -90 down here. And so -36 is somewhere between 0 and -90. It's down here in the 4th quadrant. And that says to me that we are pointing in the correct place. This angle is in quadrant 4. And that means that our theta is, in fact, this angle, 36.9. We don't need to do any adjustment. So, with that in mind, we can now put together the polar form. It's 4 minus 3i is equal to our r, which is 5, times cosine of -36.9 degrees, plus I times sine of -36.9 degrees. That is the polar form of this complex number 4 minus 3i. All right, that's it for part C. Let's move on. Here is our part D. Now, D is just -4i, and this is one of those ones where they're trying to confuse you with the simplicity of it, because -4i, it's not totally clear. Is this of the form a plus bi, question mark? And the answer is yes. It's just good to notice. It might even help to write it as the a is 0. So this is 0 minus 4i. That's the same thing as -4i. And this allows you to clearly see that our a is 0 and b is -4. Now, what quadrant is this in? -4. So the x is 0 and the y is -4. That means it's right here on the y-axis or on the imaginary axis. Down here at -4, that's -4i, which means that it's not in any quadrant. It's on the border between quadrant 3 and quadrant 4. So this is quadrant 3, this is quadrant 4, and this guy is right in between those two quadrants. Okay. Let's go ahead and find the polar form of this. Let's start with the modulus. R is equal to radical a squared plus b squared. Well, a is 0 squared plus b is -4 squared. And this is just going to be the square root of 16, which is 4. So r is equal to 4. You can also tell just by looking at the picture that when you draw a line from the center down to here, it's going to be a distance of 4. So that's all that this reflects. R is equal to 4. With that observation in mind, we could have figured out the modulus just by looking at this, because here the distance from there to there is simple. Okay, and then similarly, if we say that tangent of theta is equal to b over a, well, that's negative 4 over 0, which is undefined because we can't divide by 0. Now, this seems like it would be a problem. How do we find theta if the tangent is undefined? We can't use the inverse tangent. But it's worth noting that there are places in the unit circle, there are two places in the unit circle where tangent is undefined, and they're both where the bottom is 0. They're going to happen here at 90 degrees and down here at 270 degrees. Those are the places where tangent is undefined. And because of that, we can tell just from the picture that the one that we want is the one that goes down, and that's the angle 270. So here we have theta equal 270 degrees. If you had instead said this angle sort of going in the negative direction, this is the angle negative 90, that would work as well and gives you exactly the same answer, although it looks slightly different. There, theta equal negative 90. It's up to you which one of these to choose. Those angles are pointing in the same direction. So the modulus of this is 270 degrees. I'm sorry, the argument of this is 270 degrees, or if you prefer, negative 90 degrees. And let's go ahead and write this thing in polar form. Negative 4i is equal to the modulus 4 times cosine 270 plus I times sine 270. That's our polar form of the complex number negative 4i. All right, that's it for this example. In the next one, when we come back, we'll look at transforming complex number the other direction, starting in polar form and moving to standard form.